professors. Our topic is investigation of random mutation of dengue virus and the application of vaccine design. Since the process of vaccine design takes a lot of time, so this study provides a systematic way to know more about the structure of viruses. Motivation. In 2015, Sanofi launched a dengue vaccine, which obtained marketing authorization in Mexico. At the same time, an outbreak of dengue fever occurred in Taiwan. We expect the vaccine can be applied for Taiwan, but most of the subjects were in Central and South America. This makes us curious about whether this vaccine can be applied globally or regionally. Besides, Zika disease is epidemic all over the world recently. Since most of the symptoms and the structure between Zika and dengue virus are similar, these are their structure, almost the same. So we conduct this study to explore whether Zika and dengue virus are common origin of evolution. There are 4 objectives in our study. First, verify if the pathogenic areas of dengue virus from different regions are truly different. Identify the composition of regional evolution and label the host-induced protein on the 3D protein structure. Second, compare our results with the biochemical results. If they are similar, it proves that our method is truly effective. Third, investigate whether random mutations exist in the evolution of dengue virus type 2. If exists, it shows that the systematic way in our study is needed because the mutations are unpredictable. If none exists, maybe we can make a prediction. Fourth, discuss the origin of Zika virus and if there's a phylogenetic relationship between Zika and dengue virus. Materials and methods. We use dendrogram analysis to explore whether the mutations of dengue virus type 2 are related to geography. We collected 25 sequences from Asia, America, Africa, and Oceania, and then did an alignment with the cluster X. Cluster X is a program designed to do sequences alignment. This is its interface. It shows up the nucleotides with different colors and the mutational degrees with different symbols, so we can easily know the information of mutations. The clustering algorithm we use is neighbor join method, which can compare the sequences and then put the results into the evolutionary dendrogram. By the dendrogram, we can easily find out whether the mutations of dengue virus type 2 are related to geography. We use bar chart analysis and the structure of 3D protein to make an application to vaccine design. There are 4 steps to follow. First, according to reference, use NS1 protein to design a vaccine to reduce the incidence of dengue hemorrhagic fever. So we use the website of Thyroid2 to find out the sequences coded for NS1 was located in 775 AA to 1124 AA, and then did an alignment with the cluster X. Second, coding and weighting the results with the mutational degrees, and then sum up, like this, we coding and weighting a number. And then sum up each epitope to determine which epitopes were of greater mutations. And then label the epitopes on the 3D protein structure. Third, we classify the sequences by different regions and generated a bar chart with the sum of coding numbers. And then we conducted an overlay analysis between these bar charts. So by this step, we can easily find out the intervals with regional mutation. By the second step, we find out the intervals which are easy to divergent evolution. The fourth step is to make a cross comparison between our results and the biochemical results. This can prove whether our method is effective. The run test is used to explore whether random mutation exists in the evolution of dengue virus type 2. It's applicable to unknown population distribution, since the distribution of dengue virus type 2 sequences is unknown. So we can use this method to proceed our study. Now my partner is going to talk about our study results.
Our study results, first, dendrogram analysis. Please look at these two figures. These are rooted dendrograms. The branches are able to be grouped into Asia, America, Oceania, and Africa. And sequences show geographic relationship also belong to similar branches, so it confirms that dengue virus type 2 is biogeographic. Next, bar chart analysis. This is the bar chart generated according to what we have mentioned. We use different numbers to classify the mutational gene, different degrees of mutation. To classify the degrees. To classify the degrees of gene. And we overlay and compare with each of the continental bar charts. Asia green, Africa blue, America pink, Oceania the yellow one. And it is clear that the epitopes they protrude are different, so it proves again that dengue virus type 2 is geographic. And we can also observe which epitope is more likely to undergo divergent evolution. Professor Lin proposed 90 to 270 intervals are the significantly mutational intervals, and it's the light yellow part. The orange part is the intervals we proposed. The overlapping rate between our study and Lin's pattern is approximately 68.4 to 80.4%. And what factor causes the differences? Because of the samples Professor Lin used were only from Taiwan, but the intervals we used were from all around the world. So of course there are differences. And the intervals we propose may be more effective to the other races in the world. We reduce the intervals to these 7 sectors, which improves the accuracy. Now please look at these 3 figures. These are 3D protein structure. The pink dots we labeled on clearly show where the intervals are, and the yellow model shows intervals with significant difference. Significant difference means it's the green and red part, means the sum of it is above 10. And the green model shows intervals with significant difference and overlap with the pattern, so it's only the red part. The purple model shows us intervals with insignificant difference, means there is no protrusion in the bar chart. The sum of it is 0. So they are less prone to mutations and less susceptible to biogeographic influences, which a universal vaccine may be developed. With non-parametric statistics, the bar chart shows where the if the epitope mutated. If there is no protrusion, we use the number sign 0 to represent it. If there is protrusion, we use the number sign 1 to represent it. So we had 293, 0, 57, 1, and 97 round lengths. After bringing the data into the round test formula, we get a nearly normal distribution value Z, and the value is nearly 0.11. And because the value is between 1.96 and negative 1.96 of standard deviation, so we accept the null hypothesis and indicated that dengue virus type 2 occur randomly. So geographic relationship analysis between Zika virus and dengue virus. We compare 25 strains of dengue virus and 18 strains of Zika virus. Though it seems like they are so different, but it's just because the similarity between the same kind of virus is too high. The structural similarity between Zika virus and dengue virus is approximately 40 to 50%. And our research indicated if there is more than 30% of similarity between two viruses, and they will be highly homologous. So if Zika virus really evolved from dengue virus, then it is the most possible that it mutated from the 2 African strains, Nigeria and Senegal. In conclusion, we verified that dengue virus type 2 is biogeographic. identify the intervals for vaccine design and label on the 3D protein structure, calculating and verify the occurrence of random mutation, and systematically investigated the genetic relationship between Zika virus and dengue virus, all due to modern computational mathematics. We also combined with the subsequent biochemical experiments to make sure our study is correct. Because of the random mutation and file geography, so a systematical way to produce vaccine is more important. So if we use the methods our study proposed, it will be more efficient and effective to the design of vaccine. This is our reference. Thank you for your attention.